CademPVD, very intelligent, very easy. CademPVD, design equipment quickly with minimum inputs. Brought to you by CADEM Softwares. www.cadem.net. You are requested to watch this video in full screen and high resolution. Welcome to CademPVD. In this tutorial, we will design a reaction vessel with an agitator shaft. This reaction vessel has a top and a bottom dished end. The jacketing is of a plain shell type, partially covering the main shell and extending onto the bottom dished end. It has an agitator with 20 HP power and an agitator shaft RPM of 100. All the components in contact with the internal process liquid are of SS316, and the jacketing is of SS304. You can also view this tutorial on an HTML webpage on the link in the description. You can download a trial version of CademPVD from our website and try out this tutorial alongside by yourself. To begin with, first select the submenu option, Reaction Vessel, available inside the top menu, Equipment. This will open up the Reaction Vessel configuration dialog box. Fill in the relevant details in this dialog box. Please ensure that you select the appropriate power, RPM, duty factor and other inputs as indicated. Depending on the entry in the field, duty factor, the appropriate design safety factor is considered while designing the agitator shaft. If the internal liquid is of a watery type, then one can choose light or very light duty. In case the internal liquid is of a highly viscous or of a gummy type, then the duty factor should reflect this and the selection could be heavy duty or severe duty. The fields, life years and hours in a day are the expected working years and the daily hours of operation. These inputs are used to calculate the number of million revolutions to which the bearings are subjected. These number of revolutions along with the loads are used in the appropriate selection of the bearings. We are choosing a shaft with a single impeller, hence the number of impellers is set to 1. Set the option prop to true. This will provide the shaft with a bush support at its bottom free end by changing the configuration of the shaft from a cantilever to a simply supported shaft. Since this vessel's axis is vertical, the dialog's definitions, the front end and the rear end refer to the top end and the bottom end respectively. Set the front end flanged entry to true. This will ensure that the top dished end is connected to the shell through a body or a girth flange. This will help in the disassembling of the shaft assembly. Click on the dialog button, OK. The equipment will be added to the Project Explorer under a newly created project, with the equipment name, Reactor R101. You can see that under the entry Reactor R101, a tree list is generated wherein the various details for the equipment can be seen, defined and updated. Enter the project details in the Properties window. Click on the entry, Reactor R101, which is a major definition entry, wherein the major configurational or dimensional details are defined. Enter the contents in the Properties window. The next step is to input the design data information. For this, locate the tree node subentry, design data, and then the shell design data subentry within. First enter the shell side operating and design condition data. Note that the pressure units are kilogram force per square centimeter gauge. Having updated the operating condition information in pressure and temperature operating, proceed to updating of the design condition information in pressure and temperature design 1. If the user desires a hydrotest pressure greater than that required by the code, he can update it in pressure and temperature hydrotest. Click on the tree node, Radiography, and update the appropriate entries therein. Since the corrosion allowance is 0, there is no need to update the corrosion allowance. This process completes the definition of the shell side design data information. Now proceed to defining the jacket side design data. If the user desires a hydrotest pressure greater than that required by the code, he can update it in pressure and temperature hydrotest. Since the corrosion allowance is 0, there is no need to update the corrosion allowance. The user can edit the wind and seismic code parameters if required. The user can also change the wind and seismic code if required. The next step is to apply the materials of construction for the various components. You can define this in the common areas, thus saving time required in defining the material for each individual component. The definition of the materials is covered under the Equipment subtree, Material Specs, in the Project Explorer. The Material Spec combo box on the left side vertical menu strip lists predefined material specs or datasets. On selecting a material set from Material Specs, suitable materials for parts such as the body flange, shell, head, supports, lifting lugs, etc. are automatically selected by the software. The user can edit the materials for individual items after selecting a set from Material Specs. The user can also define his own custom material sets. Let us begin defining the materials for the main vessel components. For this, select the Material Spec combo box on the left side vertical menu strip and select from the list of predefined material specs or datasets. Update the external gasket material for the main vessel. Let us change the flange material to forged SA182F316 and change the type of the flange from a plate ring type to a fabricated weld neck type for the closure flange and shell flange objects. The materials of construction of the components which come in direct contact with the internal process liquid are of SS316, and the material of construction of the jacket is SS304. Similarly, you can now proceed to selecting the materials for the shell connections, jacket connections and the agitator system. Choose the material specs SS316, SS304 and SS316 for the shell connections, jacket connections and the agitator system respectively. In following the entire process, we've defined the equipment configuration, its overall dimensions and defined the design data like pressures, temperatures and various conditions, radiography, corrosion allowances, and have defined the materials for the various components. While following this procedure, you may have noticed that you have done minimum definitions or entered minimum inputs. The other entries have been left blank or empty and the software will select the appropriate values for them. At this stage, let us proceed to the design of the equipment. Select the submenu Design Equipment in the top menu Design Model to begin the design of the equipment. While the equipment is designed, any design warnings or errors that occur are displayed in the Errors and Warnings window. The warnings are displayed in black color and any severe errors are displayed in red. In the case of warnings, the user can review them and take necessary corrective action if required. While in the case of errors, the user has to take the necessary corrective actions for the equipment design to proceed further. You can notice that there are certain warnings only and there are no errors displayed in the Errors and Warnings window. Click on the dished end front object and generate the report for it by selecting the submenu, Code Report under the top menu Create Report. I will unpin and pin this Properties window from time to time, so that you can see the report clearly in my video. Similarly, generate the report for the shell flange front object. Click on the shaft object and generate the report for it. Similarly, you can generate the report for the other items, like the top and bottom bearings, lifting lugs and lug supports. The software has automatically selected the appropriate types and dimensional configurations for these objects.